Hello! So for this video, we will discuss about analysis of variance. In as much as the first parts of this set of slides were discussed the last time, but I will be rediscussing it again in brief in the hopes for a continuity. Okay, so the last time we discussed in full about t-test when we tried to compare measured variables, wherein the measured variables are coming from two groups or at least two sets of data coming from one group. But for this one, we will be discussing about analysis of variance, or ANOVA for short. When we talk of analysis of variance, it can either be one-way analysis of variance. Another term for that would be simple ANOVA, or it could also be factorial ANOVA or two-way ANOVA. There are instances that you may find in literatures that they refer to ANOVA as a K-sample case test, indicating when we say K-sample, it indicates that it can take on more than two, so it can be two or more. So when we talk of analysis of variance, it is defined as statistical method used to test differences between two or more means. So say for instance, we would want to see if different smiles can impact the leniency or a measure of how lenient the judgments were towards the person who is wearing the different smiles. So when we talk of analysis of variance, we can either compare all of the four types of smiles in terms of their leniency, or we can compare just either two or more types of these smiles. But we try to recall that when we talk of comparing groups, t-test is used to compare if we have two groups, correct? If you can remember that one. So why is it that analysis of variance can still be used for groups which has two or more levels or groups? So we'll try to go back to discussing errors. So if you can recall, we have discussed this before. Type 1 error happens when we say that the alternative hypothesis is true. We are assuming that there is a difference when in fact the null hypothesis is true, meaning there was actually no difference. Or it could also be that the source of error or type of error would be we are assuming that there was no difference, so the null hypothesis is true, when in fact there was actually difference, or the alternative hypothesis is true. So because of these concerns, analysis of variance is actually a stronger, more robust test than t-test. So which is why researchers actually would rather use ANOVA over t-test even if they are only comparing two groups. So let's try to remember that one. So I have been using the term earlier, one-way ANOVA and two-way ANOVA. So what does the word way in ANOVA refer to? This refers to the number of independent variables or sources or causes of the variations. So, for instance, one-way ANOVA has one independent variable, and then it has to have at least two levels or two groups that we are comparing. Two-way ANOVA, on the other hand, has two independent variables. So there are two sources of variations. And each of these independent variables will have at least two levels. So what then does this groups or levels mean? Groups or levels are different groups in the same independent variable. Another term for groups or levels would be treatments or conditions or even treatment conditions. So for example, for one-way ANOVA, we have one independent variable which is shampoo with dependent variable of softness of hair. So for this specific scenario, we would want to see if different types of shampoo can cause different types of softness of hair, or what are its effect to the softness of hair of the respondent. So the levels of shampoo would be the brands of shampoo like Palmolive, Pantene, Sunsilk. Later on in your experimental psychology, you would also be exposed to different, how to create variations or how to create the levels of your shampoo. So for this specific one, we are shown here levels being the brands of shampoo, but levels can also be literally as measured in volume. So let's say, for instance, all there is only one type of shampoo brand, let's say Pantene, but one group will take on 1 teaspoon of shampoo. Another group would be 2 teaspoons of shampoo, and another group would be 3 teaspoons of shampoo. So anyway, let's continue. For two-way ANOVA, we have now two sources of variation, which are IV number 1 is shampoo, and IV number 2 would be conditioner. Still, our dependent variable would be the softness of hair. So as you can see here, for every independent variable, we have variations of the levels. So for shampoo, we have different brands of shampoo, 3 different brands of shampoo. And for the conditioner, we have 2 levels of, we have 2 brand, sorry, we have 3 brands of conditioner rather. So now we try to look into the limitations of one-way ANOVA. So one-way ANOVA will tell you that at least 2 groups are different from each other, but it won't tell you which groups are different. So unlike t-test, wherein the hypothesis can be tailor-made according to what the researchers what the direction the researchers would have to look into. So let's say, for instance, if the researchers would want to look into significant increase on a certain variable, then they can indicate that in their hypothesis. However, for one-way ANOVA, it will only indicate significant differences. We are only looking for significant differences. So that's the major limitation of one-way ANOVA. However, that can be remedied by using post hoc analysis. So when we talk of post hoc analysis, this is a test conducted after having seen that there is significant differences among the groups that we have compared. Once there is a significant difference among the groups, then we can conduct post hoc. But thankfully, because of statistical programs, the post hoc analysis can be included already as a command in terms of how you can go about the post hoc analysis. If you may wonder what these parametric tests indicate, this one, another type of or another differentiation of statistics would be parametric tests and non-parametric tests. So when we talk of parametric tests, these are tests which involves or which concerns characteristics of the population. So given that a set of sample is randomly drawn from a population that is understood as normally distributed. However, there will be instances wherein your respondents will be purposively selected. Maybe because of certain characteristics, we only select that specific group. Or maybe for some reason or another, we cannot randomly select groups. So we have to use non-parametric tests because we did not randomly draw them from the population. So going back to post hoc, if our groups are assumed to have equal variances and they are of equal sample size, let's say for instance, for our shampoo example, the groups who would use Pantene will be 30, and the groups that would use Palmolive would be 30, and the group that would use Sunsilk will be 30. And then they are drawn from a population, from one population, so they are assumed to have equal variance. So if that is your scenario, then you can select from these post hoc tests. Usually it's Chuquet that's being used. However, if your respondents, even if they are drawn from the same population, so it's assumed that they have equal variances. However, for some reason or another, you have unequal sample size. Maybe along the way, some respondents withdraw from the research, so there is already an unequal sample size. Maybe for one group, there are only 15 respondents. For another group or level, there are 25. And then for another group or level, there are 18. So we have unequal sample size. So again, we select from either of these tests. And then a third possibility is for some reason or another, we cannot select our respondents from one population. So perhaps instead of simply saying that your population is coming from Xavier University College of Arts and Sciences, because you still lack respondents, so you go outside of Xavier. So maybe you go to another university or college. So the unequal variances would be assumed. And then also there is the possibility that there is unequal sample size. So you select either of these post hoc tests. So what are the assumptions that we take on when to use one-way ANOVA? When we say assumptions, these are the conditions that we have to meet in order to know if we can use one-way ANOVA as the test statistics to check on the differences of the treatments or groups that we are looking into. So number one is normality. That there should be normality in terms of the distribution of the population, that each sample is taken from a normally distributed population. And then there is sample independence, wherein each sample has been drawn independently from other samples. So meaning the respondents were randomly selected from a single population. And then the variances are assumed to be equal. That is, the variance of the data in the different groups should be assumed the same. So this reinforces the concept that the respondents should come from one or the same population. And then, of course, the dependent variable should be continuous. That is, the dependent variable should be measured on a scale which can be subdivided using increments like grams, milligrams, among other incremental measurements. So let's take on this sample problem for a one-way ANOVA. The problem is there a significant difference in the leniency of judgment depending on the types of smile an accused wear. So our hypothesis would indicate, specifically for our null hypothesis, it indicates that the mean for the first group is just equal to the mean of the second group, which is equal to the mean of the third group. And then our alternative hypothesis, it would indicate that the mean of the first, second, and third or groups are not equal. For one-way ANOVA, there is not much differentiation in terms of signifying or symbolizing the hypothesis in its statistical form. It is always like that. For the null hypothesis, the means of the groups is just equal to each other, and then for the alternative hypothesis, that the means for the groups are not equal with each other. So, going back to the problem, let's try to identify our independent variable and our dependent variable and how we will apply for the levels. Our independent variable indicates that the source or the reason or the cause or the preceding factor, sorry about that, the preceding factor for this scenario is the types of smile. So we would want to see if the types of smile can have a significant effect on the leniency of judgment. So to operationally define the types of smile, when we say operational definition, it simply indicates that for IV, this is how it is varied. So referring to the picture that was presented to you earlier with the man with glasses and have 4 different smiles, the levels then would be, number 1, the false type of smile. Level 2 is the felt type of smile. Level 3 is miserable type of smile. And these 3 levels, 1, 2, and 3, are called treatment groups because there is the presence of the type of smile. On the other hand, level 4 is there as a control group, or the group that has been presented with a neutral expression. And then, for the dependent variable, the dependent variable is leniency of judgment. The operational definition for dependent variable is it should indicate how it is measured. So for this research scenario, it's measured using rating scale from 1 to 5, with 1 being judged leniently and 5 being judged harshly. So if we were to understand the research scenario for this one, is that a group of people, specifically 4 groups of people, were presented with 4 different smiles. So respectively, one group were presented with 1 specific type of smile. And then after they were presented with that with a picture of that specific smile, they then judged the person in picture, assuming that he is an accused, and then they passed judgment. And then the judgment that they have given were either interpreted as lenient or harsh. So that's the scenario. So this is just a problem, huh? And then another possible problem for an ANOVA is, if you can recall, this is another example of ANOVA, even if we only have 2 groups. So if you can remember what was said earlier, that one-way ANOVA can actually be used to test the differences of at least 2 groups. So this is an example. So the problem is there a significant difference between the sprint time of athletes and non-athletes in a 100-meter dash? And then our hypothesis, the null hypothesis would only indicate equivalence of the first and the second group. And then for the alternative hypothesis, it would indicate non-equivalence of the mean of the first and the second group. So our IV here is being an athlete. So our levels then would be the athlete group, and then the second level would be the non-athlete group. And then the dependent variable here is measured in minutes. Using the data for the athlete and the non-athletes, this one is on how to do ANOVA using SPSS. Again, this is for SPSS. These are now the results table as produced as an outcome from the SPSS process using analysis of variance, which compared the athletes from the non-athletes in terms of their performance in a 100-meter dash sprint. So as we can see here, the first table, we can see the descriptive statistics with the N or the sample size for each group. And the mean time that they have, as you can see in the meantime, the non-athletes have 7.056661 minutes, with the athletes clocking in at 5.36413 minutes in their dash. And then with the deviation, for the athletes, they are being more deviated in terms of their clock time as compared to that of the athletes. So, if we would look into the test of homogeneity of variances, we can see that the Levin statistics is significant. Again, we can say that it is significant because it is below 0.05. Again, because Levin's is a test to see if they are homogeneous or not. Given that there is significance in Levin's, meaning they are significantly different, meaning the data that was gathered or the data that we have for this specific statistics problem is different. So it did not meet the requirement to use ANOVA na dapat homogeneous ang atong data. So because of this, we have discussed this in the t-test, wherein instead of using ANOVA or the ANOVA table, we go to the robust test of equality of means table, this one, the last table, in order to determine if we have significant differences in the performance. Again, if table number 2 would indicate that the significance here for Levin's test statistics for homogeneity of variances is significant, it would mean that there is significant differences in their homogeneity. So they are very much heterogeneous. And if that's the case, we go to the robust test to check on if indeed the athletes significantly differ in their sprint time from the non-athletes. We do not use the ANOVA table in this situation. So if ever the Levin's test is not significant, meaning it's 0.05 and above, then we can use the value as indicated here. But again, since it's not, so we use the values here. So specifically, so we choose whether Welsh or Brown Forsyth. Again, many people would prefer Welsh and say it is better. But if sample size is very small, meaning the sample size is lower than 6, then you can use Brown Forsyth. So to interpret the data here, or to report the results rather, we indicate that there was a significant difference between the sprint time of athletes and non-athletes at 0.05, with an F statistics of 3.15 and a probability significance of 0.000 with a minute mean of 7.06, and non-athletes took longer to sprint compared to athletes whose minute mean was 5.36. So if we have to locate where they are coming from there. The values are from there. Okay. Now, if ever you use the post hoc condition, if you can recall in the earlier slides, we use post hoc analysis, especially if we have 3 or more levels for one independent variable, so that we are able to see which groups have significant differences from each other. Because I recall again, one of the limitations of ANOVA is that it will not indicate which group is bigger or higher, or where the location of the differences is coming from. It only signifies differences, but not whether it increased or decreased. So going back, if you have a post hoc condition, you will include the post hoc results in your interpretation, specifying from data as used in the descriptives, the first table of the t-test. So as you can see here, this is a different example using sugar conditions, not the athletes versus the non-athletes. But in any case, when we try to report post hoc condition results, we make use of the mean and the standard deviation. So apparently, from the mean and the standard deviation, we can see already which perhaps have differences already. So for this one, the sugar condition was significantly different from that of the no sugar condition, which the mean is 2.2 as compared to the sugar condition, which is 4.2. And then, however, the little sugar condition with a mean of 3.6 did not significantly differ from that of the sugar and no sugar conditions, as with mean and standard deviation as indicated in the earlier statements. So what's the way of reporting the results? This usually comes after the statistics tables were presented. And in as much as there are different ways of presenting the results, but this is a usual presentation. Specifically, there was a significant difference between the sprint time of athletes and non-athletes at probability of less than 0.05, with an F value coming from 1 df and 356.54 sum of squares, which is equal to 315.63 F statistics and probability of 0.000 with a minute mean of 7.06. Non-athletes took longer to sprint compared to athletes whose minute mean was 5.36. Again, only if you had post hoc conditions, you will include the post hoc results in your interpretation. So this is again coming from the former pages. So you declare post hoc comparisons using the 2K HSD test indicated that the mean score for the sugar condition with mean of 4.2 and standard deviation of 1.3 was significantly higher than the no sugar condition at mean of 2.2 and standard deviation of 0.84. However, the little sugar condition with mean of 3.6 and standard deviation of 8.9 did not significantly differ from this sugar and no sugar condition. So again, as I have indicated, it does not have to be specifically worded in this way, but the values that are indicated here should be present. Even if for us, perhaps for readers, they would want to first go directly to the significance value, whether the P is less than 0.05 or not. But it's also necessary, it's very necessary rather, to include all of these values because it can allow the reader to locate the differences from in terms of the levels where they are coming from. But another way perhaps that can help you exercise in terms of how to report results of statistics and ANOVA specifically is try to go through different studies which used ANOVA and look at the differences or at least the different manner and different ways in presenting the report or reporting the results. Okay, so we will end in this video for ANOVA. For the two-way ANOVA, we will have a separate video. Thank you.